work with improving as a consultant. I've also worked at Google in the ads group. I've worked on autonomous vehicles, and also co-founder of a robotics startup here in Calgary. My info is there. If you want to follow up and chat later, please connect with me or send me an email. I'm happy to have a discussion with anyone here. So over the next hour or so, I want to go through some of the ideas of things that can go wrong with your models and the need to monitor and iterate on the models. I'm going to go through progressively 3 different examples, starting with a fairly simple example about a machine learning model, and then we'll build up on that to look at the need for additional monitoring and how we can actually understand what our model is doing in a production system. So let's start with the kind of a classic example, very simple predictor. If we look at house prices, we have a set of input features. It could be the geographic location, the square footage, number of bedrooms, bathrooms, if it has a fireplace. From these features, we're able to predict a price, a sale price for this house. The machine learning model is able to be trained on historical data. It's easy to observe the properties of a house and look at past sales of that house. And we could do this for an entire community or an entire city. From that, we can then learn the correlation between all these features and the sale price of a house. So this may seem a very simple example. We want to start here and talk about some of the challenges we may have around the input data and what may happen over time. So out of this data set here, what I'm looking at is the number of sales of houses with different numbers of bedrooms. So we have 4 years, and it looks like over the course of those 4 years, the sales have increased. But the demand for a certain number of bedrooms has stayed fairly consistent. So we're centered around the 3-bedroom houses, and there's a reasonable number of sales with 2 and 4 bedrooms. Outside of that, it tapers off fairly quickly. So this looks like a fairly reasonable trend. More sales in this city, some more interest over time, but there's nothing really saying that there's a change in our data. So if we monitor this, we could say our data distribution is fairly consistent for this particular input feature. Now, if you look at a following year in the dark shaded area for this data set, what we're seeing is significant change in the input data for our model. So suddenly, 4-bedroom homes have become much more popular. There's a larger number of sales of 4-bedroom homes. It may have taken away some of the 3-bedroom home sales and moved it to 4. Now, the area under the curve shows that the total sales is probably still increasing compared to the prior year. However, there's something happening in this distribution of our input data. Now, we need to understand what happens. If there is a shift in the input data, this may affect how our model is able to make predictions. So in this case, is it that maybe there is a new community being built and they have a completely new set of houses they're building with 4 bedrooms, and therefore those are selling and taking away from the sale of older homes that had 3 bedrooms? Now, the new construction could have a completely different finish. New style houses, more of an open design, and they have a higher square footage in general. Maybe they have a second story. So there's a number of changes in the concept around the house, how they're built, what is being designed there that affects the number of bedrooms. And therefore, our model that is depending on a particular set of features, right? We talked about the square footage of the home, the number of bedrooms, maybe the style of house is an input feature. Is it a ranch style house or a 2-story home? So those can be affected. And in monitoring this input data, even just the number of bedrooms, gives us a hint that something is changing in our particular model. And we need to pay attention to this. Now, it could be also that older homes are being renovated and they're adding an extra bedroom. So total square footage doesn't change for the home, but now there's a 4th bedroom being added in. And this would then affect our model. It's no longer able to predict accurately. The same square footage now has a different number of bedrooms. And so your model may be off. Now, we also need to look at potentially just supply and demand. If there's a shift towards the 4-bedroom homes and there are less sales of the 3-bedroom homes as there were previously, that's going to put downward pressure on the prices of the 3-bedroom homes. And so your model that's trying to predict for a given market, I mean, let's say a city or a small city that we're working with, the model is now going to expect the higher price based on prior training data. And so while this graph and the shift to 4-bedroom homes in and of itself doesn't tell us how the model is going to change or the exact effect on it, it is an early signal that something is happening that we really need to pay attention to within our model. Now, if we shift to a different feature, sorry, this is the output of the model. So this would be labeled data for training or the predictions from your model. And again, on the y-axis, I have the count of number of sales. So we can see here over the 4 years from our data set, and these are different 4 years than the previous graph, we can see here that a lot of the homes are selling in the $130,000, $150,000, and even up to $200,000 range. And each year it is fairly consistent. There are some small variations and spikes in different areas, but it is a fairly consistent distribution. Now, if you look at the years here, we know intuitively something happened in 2008. If we look at market data, we can see a significant drop in real estate in 2008. And some cases here getting close to 20% on some of these indexes. So from growth of 15% down to negative 20. What is this going to do to the predictions that we have? So what we would see is the following year is the distribution of sale price has now gone down and to the left. It's the dark shaded area again. This is an indication that something has happened with our model that we need to pay attention to. It doesn't tell us what specifically happened or why it happened. We have to look for external sources of information for that. However, there are different explanations, some of which may affect the model, some of which may not. So with the curve going down, lowering on the y-axis, it means there are less sales. Now, in and of itself, that may not significantly affect our model. If the lowered sales is just a little bit slowing of sales, but it doesn't significantly affect the price of homes, your model may still be accurate. However, if the drop in sales also puts downward pressure on the price, it means that the same house before is now selling at a lower price. And so that would start shifting this curve. Now, there may also be a lower demand for homes that are in the higher price ranges. So potentially people are simply wanting to buy homes that have a lower price already. And so there are different factors here, and we're not necessarily going to be able to tease them apart. And that's really not the purpose of the exercise. What we want to look at here is understanding that if we look at both the input features and the predictions of our model as a distribution, and ideally we could do this in real time, is to look at this and understand there is now a shift happening. My input data no longer follows the expected distribution. The predictions no longer match our historical set. And so in this case, our model was trained on a given price X for a house, whereas the new predictions really should be 80% of that. And so further in this talk, I want to dive into a little bit of how we actually deal with these particular changes. Now, we've talked about the input and output features. There's something to be aware of in your data. Now, if you have, for example, trained a model and you say, I've got 3 months of data, that you have a fairly high number of transactions, say on your website, and you're able to pull in that data and train a model. The problem is 3 months of data may be enough to train a model that looks like it has high accuracy. However, you're missing out on some seasonal changes. So this is some data. It's out of the US. And so you can see here different events throughout the year are producing very different shopping patterns. And so if you trained on 3 months of data, let's say January, February, and March, you've actually missed all of these particular events. Now, if you happen to train with April, you might catch Easter. Or if you trained with August and September, you've got back to college, back to school, the two combined there. Your model is going to be able to learn across that. However, it may be biased towards those particular events. And so when we think about seasonality, we have to look at what is the time range that our model is training on. And it may be not as obvious as shopping trends. It could be, for example, here in winter, it's hard to view homes. Maybe people aren't buying as many houses in the winter, or if it's really cold, people less likely to go out and shop. And so there are going to be seasonal variations that may not be tied directly to holidays, but could be tied to weather patterns. And so we need to have an awareness that things will change and start training models that are able to look at a time range that covers all of the possible seasons or variation in some of our input data. And so if you look at shopping throughout the year, ideally we would train a model with a minimum of 12 months, but maybe 13 or 14 months total as a sliding window. So if I train on the past 14 months, I'm covering all of the seasonal events that are occurring, and they can all help inform my model. There are other cases that are not as obvious, and it's just this one-off during the year, where in this case, like Halloween, pedestrians look like pedestrians, most of the year. And even on Halloween, most pedestrians still look like human shapes. However, when you get to children out trick-or-treating, they may be out in costumes, and suddenly the shape of a human is going to be very different, and your object detection is not going to work as well. So this is actually a real photo taken at Waymo, where they had a parked vehicle to collect additional data. And so being aware of the seasonal variations, you're able to, ahead of time, collect data that can help inform your model and build a model that's more robust to children that are out trick-or-treating. So now they can be classified as pedestrians accurately, even though they may look like a giant sphere or a very blocky character. So when we talk about mitigating seasonality or any sort of variation in our input data, there's really two options: train a better model or acknowledge that there is risk and detect it. Now, as much as we would all love to be able to train a perfect model, it's like writing perfect code with no bugs. It really doesn't happen. And so the only solution that's practical is to acknowledge that there is risk from seasonality or factors that we haven't thought about, and create a system around our model that allows it to detect these changes and adapt to it as it's happening. And so the rest of this, I really want to focus on this monitoring, learn from that, and iterate on your model. So I'm going to shift to a second example. So let's move away from the very simplistic house price. Let's look at a web search, which is returning a variety of results. So here we have organic search results at the bottom, we have some ads, we have product placement, and we've got a knowledge card on the right-hand side. So it's a complex page, but I'm going to reduce this to a subset of this system that I want to talk about. So if we zero in on the product ads that are here, we're going to have a simplified architecture we're going to talk about in terms of the monitoring. But the basic components is that there is a database of products that exists. There is a product matching algorithm. For a given query that someone's going to put in, somebody types a query, we want to be able to match products and pull that from the database. So in this case, if they're searching for a coffee maker, we can ignore downhill skis. They're not relevant to that particular query. So we don't need all of our products to rank, but we're going to pull a subset of coffee makers that are potentially relevant to this user. And then we're going to use a model that's going to predict the click-through rate. So in the advertising space, we talk about click-through rate. What is the rate that users would click on a given ad? And so this is very informative in terms of ranking ads. So I don't want to get too much into details of advertising per se, but let's just suffice to say that we have these three components: a database, some sort of algorithm to extract products, and then a model that is going to rank the different products. So if we look at it as a basic, sorry, there's a question popping up here. Okay, what is the minimum number of factors needed to assume that a model's predictions are reliable? For example, the real estate's only had 2 factors, but that is not enough, or would you need factors like neighborhood and future prospects of the neighborhood? So to make reliability of the model is definitely a challenge. And most of what I'm going to talk about actually here, I think the next few slides will actually start to answer some of this question a little bit better than I can do as a quick summary here. What we don't know exactly in the house price predictor, what is what are the specific factors, or how do we monitor what may change? Broadly speaking, we actually want to look at a distribution of for every single feature, have a distribution of historical data and monitor that feature. And then the same with our predictions, is it following a distribution? There's a bit more to it. So let me park that. If the person who asked the question, if in a few minutes you have further questions, please feel free to drop them in the chat. But I think I'll be able to answer a bit more as we go through the next slides.
This is super interesting. That comment about the Google not or the parked car with the Halloween costumes, I thought was so interesting in the context of autonomous vehicles. It's very neat. It's something to think about for sure as a part of the risk factors within a model.
Yes, and that was just one example. There's many cases where we've created synthetic data. Effectively, it's not synthetic, it's specific data collection, I guess, to target very specific seasonal or other bias that the model has. And so there's an entire other talk we could do about bias in models and how we can remove as much as we can, and augmenting your data set. Happy to chat some more towards the end. Let's dive into a little bit more of the monitoring, because I think this will be very relevant to this question that was asked, and building out a system that helps us understand where a model may fail. So looking at the system architecture, very simplified diagram. We've got the user on their laptop. They're going across the internet. They're going to hit our server. It's going to query a product database, and it's going to use a model to rank the ads that we're pulling back. So when we talk about monitoring, and I listened to a previous talk this morning that talked about monitoring models, what are model metrics, and there's a lot of discussion and a lot of knowledge that already exists in understanding how well our model itself is performing. And if we look at the house price predictor, there's a direct correlation between the prediction it makes and the observation in the real world that we can make later on. We can predict a sale price for a house, and a month later, when the house is sold, we can see how much the house was actually sold for. We can directly link those two and say, how close was my prediction? Once we get into a complex system like this, like the advertising, where we're pulling products and we're ranking them, the model output does not directly correlate with sort of external observable behavior. The model becomes hidden within this system. And so what we need to start looking at, so we can isolate the model as we normally do. This is a fairly well understood field. It kind of follows out from the model evaluation that we do during training. We can look at runtime and say, how is our model performing? Now, in terms of monitoring, I've talked quite a bit already, I think, about looking at the input distribution. So for each feature, having maybe a distribution of values from your training set. And then at runtime, look at the features that you're feeding into your model when you go to make a prediction, and accumulate a distribution of the features from their real-time predictions and compare it to your historical set. Similar to covariance shift and other techniques that exist that are more on the model training, it's at runtime, can we actually compare this and see if there starts to be a shift in the input features, or any input feature, if we monitor them all. Similarly with predictions, what we're looking here is not to solve the problem of getting a better model. It's really to accept that models are going to have problems, and really detecting it and coming early to be able to say, we need deeper analysis. So same with predictions. Look at the distribution of predictions. If suddenly the predictions that are coming out of your model no longer match your historical set, or you see that the distribution starts to shift right or left, it's an indication something is happening and you need to look a lot deeper. So there's simple features like feature drift. You can look at even the inference of your timing. How is the model itself performing from like CPU or timing? If my prediction is taking historically 1 millisecond, but suddenly my model is taking potentially 2 milliseconds, there is something there that may indicate something's wrong with that serving system for the model. So I'm not going to spend too much more time on this part. I think this is fairly well understood from a data science perspective on monitoring models. Now, what I propose is that we continue layering our monitoring and look at stepping away from the model. Let's look at the next layer of the system. So what is feeding our model? It's a user query that's extracting products from a database. So as you extract it from the database, we then rank it. And so the output from that is a ranked list of ads that we want to show. So with that, we can look at that part of the system, and without looking too deep into it, looking at the output, that ranked list. Now, this gives us an early warning about our system that maybe there's something wrong with the database. Maybe some products have disappeared. Maybe our matching algorithm is not connecting the keywords with particular products. There could be a problem on the server itself, or it could be a problem with the model that's no longer accurately ranking. So this layer of monitoring, again, does not tell us exactly where the problem exists within our system, but it is, again, an early warning system that something within our system is going bad. If you're monitoring the system at this layer and you have model metrics, you start to get information of each layer and you start to isolate where the problem is. So what I would propose at this layer is actually looking at the server, the CPU load, memory usage, I/O requests. This is part of your typical sort of DevOps for your system. If you're operating this system, you're looking at your server metrics. But I would say bring those metrics out from the more isolated operation parts of the system and say, let's surface that with your model metrics. Roll that into your real-time dashboards that help you monitor the system along with the model. And further, we can also look at product metrics. So what are the number of products that are being pulled from the database to be ranked? So before the ranking, how much are matching the query? Now, there's going to be a wide distribution. Some very niche products may only match, say, 12 items. You get a dozen out when you do a query. A very popular item, you might get 500 or 1,000 results. But that gives you another distribution. Then you want to monitor over time. Does that distribution of query results match, our historical set? And so suddenly you have a drop in number of products. And again, an indication that something may be happening within your system. And so it may not be your model that's going bad. It could be that the queries. But this gives you this information to start isolating parts of your system and have parameters that say, maybe the model metrics could be good, but maybe there's something on the serving side or that we're not feeding the right inputs to our model. So it's creating layered monitoring so you can start understanding at a higher level perspective what may be going wrong. Now, the third layer I want to talk about is actually monitoring from the user perspective. You may be able to get some great products from the database and your model is able to rank them. So the number of requests or results that you're getting from your database for a product, you may be getting a similar distribution. Sometimes distribution shifts, as we talked about with the system monitoring, but if you're getting the same number of results, your metrics may look good for the database queries, and the model may be ranking those products well. So it may look like your model metrics and your system metrics are good. However, from a user perspective, you may be matching, say, the wrong product. So if you match a product, I look for coffee makers and I'm getting alpine skis that are coming back. The model is happy to rank the skis just the same. So they're ranked, we got the same number of skis. Like if you look number of results, right? If I got 500 coffee makers, but now I'm getting 500 skis, my distribution looks good. The model ranks them quite happily, and it still matches the same distribution that you had historically. And so the problem that you're seeing within the model is actually being hidden. There is a problem in the system, but you're not able to detect it. And so having a user-facing layer is really important. What allows you to do here is to ultimately the user is kind of the labeler for your data, if you will, right? They're going to click on an ad or not click on an ad. And so while your individual metrics for the system may look good, there may be a wider problem in the system. And so if you create metrics about, say, the user's search patterns, or in aggregate, what are all the users searching for? What are the common key terms? Now you might say, let's use a kind of a bit of an artificial example, but if suddenly coffee maker queries are matching skis, something is wrong. We're going to see that the type of products we're bringing in from a user perspective is a completely different distribution. And so being able to monitor at that layer gives us the So a final validation that the whole system is working. And we can look at user engagement, in broadly speaking, to say, even though individual parts of the system work, if as a whole there is a problem, your user engagement would drop. And so some of the metrics, if you're kind of a web-based system, would be page views, right? How often is the user engaging with the site? If something is going wrong, that your ranking is off, your product search is wrong, users are going to drift away from your site. They're going to lose interest. You can look at the number of ads displayed. So maybe your product matching is working reasonably well, but you're getting less relevant products. So maybe there's less ads being shown. Is the user clicking on those ads? And so if you click on ads, the user's off your site, they may come back. If they're coming back, it's because they didn't find what they wanted, and they may click on a second ad or another search result. So you can monitor things like the time that the user cycles going off-site back to your search page to look for the next result. All of these metrics give us that insulation, if you will, that if something goes wrong, we are really well covered in our metrics. And so it's not relying about a single metric at any layer. It's about layering this all together to ensure that we cover as many possible holes we have in our logic. We may not always think about what are all the perfect model metrics, or what are the exact metrics for the database queries, right? From our knowledge of the domain, we may be able to design some good metrics to start off. But as we move out towards the user metrics, it gives us that extra kind of coverage of everything. Now, if you find a user metric goes bad, when you're monitoring, something's going on with your system, it's an opportunity to go back and add lower level metrics that are monitoring closer to the source of the data. So maybe add some database metrics, add some model metrics that help plug the holes and detect those problems earlier. But each layer that we add adds an extra layer of protection from potential mistakes or omissions that we have within our monitoring and within the model itself. Now, anybody who's done statistics, you're going to know that if you look at just the aggregate, you're going to miss things. So if we have, let's say, country A and country B that have users querying our website, maybe suddenly country A, their queries start going up, country B goes down. In aggregate, it may look like we have the same level of user engagement. And so what's important when you monitor is not only to look at the aggregate, but to actually break it down into meaningful slices. So it could be breaking out the countries or provinces or postal code to see, does that distribution hold up across all of these different slices of data? The same with demographics, maybe it's product categories. So we have maybe foods and beverages as a category, and maybe there are sports equipment. And so we're able to break that down. And so our query, where the database is now returning skis instead of coffee makers, sliced by product category, we would suddenly detect a shift. Coffee makers go down, skis went up, even though in aggregate, the number of queries may be the same. Now, this is just a sample of these slices that you'd want to look at. It's impossible to make an exhaustive list. You'd have to look at your business domain and what are some of these factors that we need to consider within our model? Look at the input features to your model. Maybe a good hint. If we look at our house price predictor, one is the location of that home. And so right away, you know there's a feature that's based on geographic location. That's a pretty strong hint that you should slice any metrics you have based on location. And so going through that list of your features, you get a hint of how do we slice our actual monitoring to make sure that it is valid and that we don't bury trends within sort of the aggregate. Now, we've monitored the model. Now, what we want to talk about is what do you do? Do we detect a problem? How do we respond to that? And I want to just put this fact out. I'm going to call this a fact. I'm not going to really debate it or justify it. I think anyone who's worked on machine learning models, you know that you need to retrain the model regularly. Now, depending on domain and how fast the environment is changing, regularly could be daily, could be weekly, monthly, once a year. That really depends on your business domain, but you have to go into a machine learning situation where you understand that you will have to actively retrain and monitor this. Now, given that, what we look at is when is the right time to iterate on this. And sometimes it may not be practical to be training models every day. That may be just too fast or have too much computing resource needs for us to be practically be able to do that. So from our monitoring, what we want to do is define thresholds on the metrics. So from the model, the system, and the user metrics, define a certain amount of drift that is allowed. There's going to be some variation in the distribution of your features, the distribution of predictions, system performance. But maybe you decide that if it's off by more, if it starts to shift by more than 20%, we have a soft alert. And if it moves more than by 20%, maybe there's a big red light going off and it's like, we really need to address this immediately. So relate to your business domain, find out what is reasonable drift to expect, and put in automated alerting. Have the system actually reach out and just raise the alarm when something starts to drift. It's not going to solve the problem, but it does give you that early indication that you need to go in and start troubleshooting your system. Now, what you can do is have another model trained in a dev environment with the latest data, right? So if you trained a model that's been in production for a month, train a new model that includes the last month of data. Now you have that model, you can compare it to your production model. Does that new month of data that you've added make a better model? Is it more adaptable to whatever trends are now happening out in the market? And is the model learning something a little bit different? So I'm going to look at, there's a few different approaches to retraining models. So one of them, the simplest approach, or the least infrastructure that you need, is if your alerts go off, you say there's something wrong with my model and I'm going to troubleshoot it, my whole system, and say this model actually is drifting. The conditions have changed. Maybe the housing market went down like in 2008 and I need a model to be updated. So what we have a production model that's serving. Now we've hit a threshold on our drift or the accuracy of the model. And so what we can do at that point is just train a new model, put it out into serving predictions within our system. So this is the on-demand model training. Fairly straightforward, and it's sort of the starting point for most projects. You do some basic monitoring, things go bad, let's make a new model and push that out. Now, there may be a certain amount of lead time to retrain a model that we need to be aware of and account for that. So if you need something to be very responsive, let's say in the advertising space, user behaviors can change daily, and we want to be very responsive. We may not have the opportunity to spend several days or a week training a new model and validating it. We want to move that out to production a lot faster. So one scheme is you can actually do a daily batch training. So if you have the computing resource and you're willing to make that investment, is every day have an automated job that goes and trains a new model with the most recent data. Now, at the end of the day, you can throw that model out. The next day, go and train another model. And now you can compare that model to the one that's actually in production. So you can actually add a new layer of monitoring, which is a comparison from your production and your pre-production model, the daily trained model. And so you can actually say, if the pre-production model, suddenly its accuracy starts to improve compared to your current production model, it's a new sign that something is going on in your system. And so you can actually use the second model as a sort of fourth layer of monitoring and validation. Now, there are some cases where you have an online training algorithm. And so you're able to feed data in real time into the model that's training. And so you have this continuous training scheme. In this case, similar concept, to have a pre-prod model that is continuously training on the data as it comes in. So either instantaneously or every hour, you're pushing in more data. And then you compare these two models. And what we have here is a decision point where the model that's pre-production is actually starting to outperform our production model by some margin. And so we're happy. We say, okay, this is a great model. Let's do some final validation. Push that model out to your serving system as the new production model. And then in the background, start training the next pre-production model so that it is ready to go the next time. What we do want to note is you don't want to be, if you have an online training system, you do not want to be constantly training the same production model that's actually used for serving. If you've trained machine learning models, you know that training is not a perfect science, right? It's training the same model again. There's always some variation one particular training run with the same hyperparameters could have a lower accuracy and just veer off into some other space. So it's really important to isolate that pre-prod model and actively validate against your production model. Okay, so for the next few minutes, what I want to do is just wrap up by looking at a third example, which is a much larger complex system. We've looked at the house price predictor, where the model output directly correlates with the real world event that we can see. It says the house is going to be priced at X. We can observe this actual sale happens at price Y, and we can directly compare it. In the ad system we looked at, you can bring in, the model is ranking the different ads, and that has a reasonable correlation to user behavior. You can make some inference that if you rank it higher, the user is more likely to click on it. And that's just observed fact that users will click on the results that are at the top or the left of the screen. So there is some correlation with your model, but as we get to very complex systems, you start to lose that correlation between a given model and the behavior of your system. So I'm going to talk a little bit about autonomous vehicles. I think it's a great example in that it is very complex. Now, it may not be something we all work on every day, but it gives us the lessons we learn from working on such a complex system, I think, apply to many other systems and really help us inform how we structure the monitoring and how we think about the models. So if we look at your average self-driving car, it's going to be hundreds of models, a very large number, right? And each one has a very specialized purpose. But each model is not directly controlling the behavior of the vehicle. Models are all tied in with other additional logic. So there's some traditional programming that's happening. And one model may rank objects. So we talk about maybe object detection, which I have a model that's going to say, these are the objects that are most important in the scene. Maybe because they're coming near me, they're going to cross my path. One model may actually rank those. Then you take the top objects that you care about, and then you apply more models to those. So one model doesn't have a direct correlation to an exact output. All of these, there's a lot of other logic and layers that are built up within the system. And with an autonomous vehicle, because of the safety concerns, there are redundant systems. There is effectively emergency braking. There's bypasses. If the model is making weird predictions, let's just ignore it, right? We're not going to completely rely on a model to drive directly the vehicle. And so with all of these additional layers that are built in, the model is far removed from the behavior that you can observe, and where the model falls kind of outside of given parameters, we're actually going to ignore the model. And so there's that cutoff where the car may look like it's behaving well, but the model is going crazy internally, and we're just ignoring it because we now know it's outside of its reasonable parameters. So we look at this system, it's how do we actually monitor these models that are within this vehicle. So I'm going to take an example. Let's say we have a cat detector and a plastic bag detector. We're trying to figure out what these objects are so that we can react appropriately. If it's one of those pesky plastic bags blowing in the wind, we don't have to take action. We continue on driving. If it is a cat, then we want to avoid this cat. So we want to slow down, maybe change lanes. We want to take some sort of action to react to it. But every action we take has a consequence in the real world. If I slam on the brakes, there's a risk of a rear end collision. And so with a plastic bag, it's not just, we can't simply say, if I detect anything, I'm going to stop. We need to be able to react intelligently and say, what is the overall risk within our system? So plastic bag, if I slam on the brakes to get rear-ended, we say that was a poor trade-off. I want to continue driving. But for the cat, it may be a reasonable trade-off to slow down quite aggressively and avoid a collision with the cat at the risk potentially of other vehicles having to react behind us. So where there are these real world consequences, we have to really think hard, how do we monitor this and understand what is happening? Now, I've talked about this. You cannot directly observe the behavior of any given model. My cat detector may be failing in saying it's not actually labeling cats properly. I don't know that they're cats. I think this cat is some snow on the road, right? The we can't really observe that. So the car's behavior may still work. Maybe the collision avoidance system is causing us to slow down. And so we're making up for the fact that the cat detector did not work correctly. Now, with a self-driving vehicle is that we're collecting data at a very high frame rate, right? Let's say you're collecting data 10 times per second. You're running through your prediction loops. That is a massive amount of data over a few hours of driving. It's impossible within a scene to pick out all of the objects and say, and manually observe and label data to say, well, this really was a cat or this was not a cat. It's massive data and it's hard to process all of that. And especially with the cat detector, this happens very early in the driving decisions. There may be models later on that talk about avoiding collisions or planning our path, right? Deciding at this point, should I accelerate a little bit or hold a steady speed? Those happen later in the cycle and correlate more directly with the driving. But the earlier you are in the driving cycle, the more disconnected you may feel. So what we're trying to do here is, in terms of monitoring in this kind of complex system, we're not going to be able to we can't monitor the model itself, right? The model is simply outputting typically a probability that this object is a cat. Now, when we're really far away, that probability is going to be low. It's going to be a fuzzier image, but as we get closer, the image gets a lot crisper. And the probability of this being a cat is going to increase significantly. So we can monitor that model and say, from perspective of, if you look at the whole system, over the lifetime of the model, in a given environment, maybe you expect a certain number of cats, but that's a pretty fuzzy picture. So how do we start to isolate this within our system? What we can do is to narrow down the amount of data that we need to look at and monitor is now you can actually use the model over time to start detecting potential issues with itself. So let's say at a distance, my model is saying this is not really a cat. I'm not sure. Maybe it's 30% chance that this is actually a cat. But as you get closer, the same object that your system is observing, now the probability shoots up to 98% that this is a cat. You can actually build a system where now you're correlating over time the predictions from your model. And so you can say, this object where I was very, very confident it's a cat, as we got closer to it, my model should have picked this up sooner. And so if you correlate those, you can actually reduce your data set and say, okay, I'm going to isolate these objects and start monitoring the accuracy given, say, a certain distance to these objects. And so maybe as we got closer, we said it's a cat, we can look back and say, what was the distance at which we determined it was a cat? And so you can add this as a monitoring metric to say this model should detect at this particular distance is typically when our accuracy goes up, say, above 95% confidence that it is a cat. So it's one of the techniques you can have to really try to isolate some of the model metrics within this really complex system.